Yeah, so in the next few lectures, we will talk about non-convex optimization applications and algorithm. Recall that in the past few lectures, we talked about MLP problem, which is a non-convex problem, but it has very nice structure because the relaxation is linear. But in general, you can deal with a broader class of problem. Let's say if we have a continuous optimization problem, minimize f of x subject to some inequality and equality constraints. Well, if H is convex, L is linear, then you are solving convex optimization problems. But in general, this constraint set can be a non-convex set. Then how do we solve this non-convex problem to global optimality? We will talk about these applications as well as algorithm in the next few lectures. First of all, I would like to show you that this is a very generic class of problems to consider. A very straightforward result is that any MILP problem is a subset of continuous non-convex optimization problems. Right? You can show this by showing that MILP is a subset of a quadratic constraint quadratic program. Why is that? Because for any binary variable, y is 0 and 1, it is equivalent to the following quadratic constraints. You just say y times 1 minus y equals to 0. It's very clear that the only two roots to this equation is 0 and 1. So from that, you can see that any MILP problem can be expressed as a QCQP problem. So a QCQP is more general than MILP in this case. Of course, if you can deal with any non-convex continuous optimization problem, then it must be more general than MILP problem. Right? Since they are more general, you can expect that solving those problems to global optimality will be more difficult than solving MILP problem to global optimality, which we will talk about in the next lectures also. Another extension to the non-convex NLP problem, of course, it's a non-convex MNLP problem. Right? Not only you have continuous variables, but you have a binary variable y as well. Okay. Now, without loss of generality, you can assume the G and H functions can be non-convex. So there's a concept called convex MINLP, meaning that if f and g are convex functions, H is linear, then it is called a convex MINLP. In other words, the continuous relaxation of this MINLP problem is convex. But of course, any MINLP problem is non-convex, right, because of the binary variable. But usually in the literature, you may find people talk about convex MINLP. What they actually mean is that if you relax a binary variable, the rest of the problems is convex. That is a convex MINLP. And it is also, you can call this non-convex MINLP, where the continuous relaxations are non-convex. Then it is called a non-convex MLP. And of course, the algorithm to solve convex MLP and non-convex MLP can be very different. Right? We will talk about some algorithm for convex MLP as well. Yeah. Any questions related to the concepts here? Okay. Yeah, so in this lecture, we will talk about a few problems where, some of the problems are non-convex problems. There are no binary variables. And some of the problems, they both include non-convex constraints and also binary variables. Okay. And then we try to make those applications as diverse as possible. There are some applications related to logistics, like packing problems and facility location problem. K-means clustering is an application related to machine learning. And then we have pooling problem in the oil and gas industry. Molecular structure prediction is some chemistry type of problems. And then finally, we will talk about an application in the chemical industry. But the tricks to solve this problem apply to a number of other problems. That's why we put it here. Yeah, so let's first talk about this packing problem. The goal of packing problem is very straightforward. Let's assume if you have a container and you try to pack as many things as possible into this container. Right? That's one of the things they solve when they have a container. And this application is related to logistics and shipping. And there are other applications of the packing problem related to manufacturing and material cutting. Right? If you think about, let's say, a manufacturing which manufactures clothes, right? So you can cut out the shape of your clothes from very huge material, but you want to cut as many pieces as possible from the raw material, right? Yeah. And then it has applications in computer science and data storage as well, right? You want to be very efficient in using your memory such that you can store as much objects as you can. Okay. But we will talk about two special cases of packing problem. Now the first application is very straightforward, a circle packing problem in a big circle. So let's assume you have a big circle and you have a bunch of smaller circles. You try to pack them. Actually, the problem is rephrased as the other way. You want to minimize the size of the big circle such that you can pack all the smaller circles into the big circle. Right? So this problem is kind of equivalent to that. If you have a fixed big circle, you try to pack as many smaller circles as possible. The formulation can be very similar, but here we just formulate it as a minimization problem. You assume the size of this big circle is not fixed, but the number of smaller circles are fixed, right? Yeah. So this application can be due to, let's say, if you want to pack some cylinders into a larger cylinder, right? Then you are essentially solving this type of problem, right? Yes.
Is this similar to the knapsack?
Yeah, so you can think about this as a 2D knapsack problem, if you wish, right? The knapsack problem only has a capacity, right? You can think about the knapsack problem as a 1D packing problem, right? You have a capacity, then you try to pack as many knapsacks as possible. But the packing problem is usually in 2D or 3D, right? Then you have to consider the shapes you are considering. Of course, circle is the easiest shape you can consider, basically. Yeah. Yeah, very good point. Any other questions here? Yes.
What do X and Y represent?
Oh yeah, so I'm about to explain. Yeah. Okay, so the X and Y are let's see. Do I have it here? Yeah, I think I do. Yeah, so the xi and yi are the coordinates corresponding to the center of each circle. Okay, I don't have it in the. Okay, so ri is the radius of circle I. Then xi and yi are of, let's say, the center of circle I, right? So let's treat the origin of the big circle as 0 and 0. And then the xi and yi are the, so for example, let's say if this is the center, and this is the x-axis, this is the y-axis, then xi, yi are the, let's say, the coordinate of the center of a given circle. Okay. Yeah. And then now let's talk about the constraints. Okay. So first of all, we are just minimizing the radius of the big circle, right? And then if you look at this constraint, this is essentially the distance of the center for a given circle to the origin, right? If you consider the the coordinate of this circle B is xi, yi, then the square root of xi squared, yi squared is essentially the distance of this center to the origin, right? And of course, if you have this center, then you have to make sure that this particular circle lives within the big circle, right? What does that mean? That means if you have the distance to the origin plus the radius of this, so this yellow point is Ri, right? The radius of this circle. The distance to the origin plus the radius of this circle has to be less than equal to the radius of the big circle you are embedding the circle within, right? Yeah, so that's what this constraint means. And then the second constraint is like a non-overlapping constraint, right? If you pick any two smaller circles, they cannot overlap with each other, right? So if you consider the right-hand side, that's the distance between their center, right? And the distance between their centers have to be greater than or equal to the two radius, right? If you consider, let's say, so these two circles, circle B and C, then their distance is RB plus RC, but the center of their coordinates have to be greater than the distance of their center should be greater than or equal to their radius. That's essentially what it says. Okay. Any questions related to the constraints? The first is just to embed all the circles within the big circle. The second says that pick any two smaller circles, they cannot overlap. Right? So if you consider this type of problem, it is very to say that they can be represented as non-convex QCQPs, right? Because dealing with square root terms is not as straightforward, but if you can do the square on both sides of the equation, right? You just move Ri to the right-hand side, then this particular constraint is nothing but this quadratic constraint here, right? You just do a square on both sides of the equation. And this constraint is clearly non-convex, right? We know that the quadratic function is a convex function. If you put a quadratic function on the left-hand side, then it is convex, but you still have some quadratic term on the right-hand side, right? That means the Hessian is not positive semi-definite. If you try to calculate the Hessian of this, it should be a 3x3 matrix. Then it is non-convex. Okay, so that shows you the circle packing problem is a non-convex optimization problem. Okay, but you can use Groovy to solve non-convex QCQPs to global optimality nowadays. Yeah. Is this part clear? Okay. Yeah, and then maybe more practical problem is that you pack some square within a rectangle. Usually the container has a rectangle shape, not a circle shape, right? Now we need to consider the rectangle shape. The problem gets changed a little bit, right? Instead of minimizing the radius, you just minimize the length and the width of the rectangle. Let's denote the A and B to be width and the height of the container. Then similarly, we have to make sure that the circles are contained within the rectangle. So those constraints make sure that all the circles are contained within the rectangle. If you want me to write it down clearly, then perhaps we have a rectangle like this. So this is not a rectangle, but you get the idea. Yeah, so now you have this is the origin of the big rectangle, but then you want to fit, let's say, a circle within the rectangle. then the coordinate x plus this is the xi, yi for this circle. Then the x coordinate plus the radius has to be within this rectangle, right? The length of this part is a over 2, right? That's a denote the whole length of this rectangle, and if you take half of that, that's a over 2. So that essentially says if you have xi plus the radius of the circle, it has to be less than or equal to a over 2. And what this constraint says, and similarly you have y plus ri has to be less than or equal to b over 2. And then this part just says they cannot, the other side cannot exceed the threshold either. So by symmetry, you can derive all the other two constraints. We also need to have the non-overlapping constraints, which basically is identical to the previous one. You have Ri plus Rj has to be less than or equal to the distance between the two circles where, yes, so let's denote the distance Dij by the square root of xi minus xj squared plus yi minus yj squared. Okay, so the Dij is the distance of the two circles, which we already have it in the previous slides. Here we just denote this as Dij. Okay. So this is essentially the same non-overlapping constraints we had in the previous slides. And maybe you have an upper bound and the lower bound of the width and the height of the container as well. So you bound them. Yeah. Okay. Any questions for this problem? Okay. Yeah. So this should be pretty straightforward. Yeah. And then another application is so-called continuous facility location. This should also be pretty straightforward. Recall that we talk about something called uncapacitated facility location when we talk about MILP problems. Recall that the idea of facility location is that you have some depots and you have some clients, right? You want to pick some depots such that you can serve all the clients, right? And then you want to minimize the setup cost and the transportation cost. But in the MILP case, the location of all the depots are predetermined, right? You already picked a subset of the depot you pre-selected. But in practice, maybe you can pick the location of the depot in a very arbitrary way, right? You can move the depot continuously on a 2D map. Okay, and that will make the problem harder to solve. Okay. Yeah, so that's a main difference. You can just pick the coordinates of a facility instead of use a binary variable to determine which facility are selected. Yeah, so maybe you don't remember the facility location, but let's just talk about what is a continuous facility location, then you can go back to the uncapacitated facility location. So let's consider a set of n potential depots and m clients. And then you have a fixed cost for setting up the depot and the variable transportation cost to, let's say, in this case, we can call it a unit, maybe a unit variable transportation cost. So the transportation cost is proportional to the distance. And the location of the depot can be selected anywhere on a 2D plane, right? We do not constrain the way you pick the location of the depot. And here we have xi, yi to be the coordinates of the ith client, right? The location of the clients are already determined on the 2D plane. We assume we already know the coordinates of the client. And in order to formulate this problem, we will have some binary variable zj to determine whether a depot is used or not. Right? You can If Z is 1, that means the depot is built, Z equals to 0 otherwise. Here, Wij represent the fraction of client's i's demand satisfied from depot J. In the previous lecture, we already talked about this fraction. So maybe do a very concrete example here. So let's say you have a client I, and then you have a couple of depot, let's say J1 and J2. Okay, and then you have W, let's say I equals to 1, then Wi I1, J1 is a fraction of I's demand that are satisfied by J1. Then we have Wi1, J2. For example, you can set Wi1, J1 into 0.3. That means 30% of the demand of this client, I1 is satisfied by the first depot. And then the rest is like 70%, right? 70% of the demand is satisfied by the second depot. That's what this W variable means. Okay. Yeah. Right. And then for all the other variables, we need to determine the coordinate of the Jth depot as well, right? So because we do not know where we are going to place the location of the depot. In the uncapacitated facility location problem, you just assume maybe you already predetermine their coordinates, and then you only need a binary variable to determine whether we are going to build J1 or not, right? But the location of J1 is fixed, okay? In the continuous facility location problem, not only you are deciding, whether you are building this J1 or not, but you are also deciding the location of J1. So in other words, a continuous facility location gives you a higher degree of flexibility, right? You can pick the location where you are going to build the depot. Yeah. So let's say, is the problem statement clear here? Yes.
So does W change based on the position of the depot as well?
Yeah, so you are optimizing the W as well, right? Yeah. Any other questions? Okay. Yes. Now let's look at these constraints. First of all, the objective consists of two parts: the fixed cost and the variable cost. The fixed cost is just Fj times Zj. That says how many depots you are going to build. Right? Remember, Zj is a binary variable that decides whether you are going to build depot J or not. Now the variable cost are related to two parts. The first is of course you have the coefficients for the variable cost, which is Cij, and then this W variable is a fraction of demand that are satisfied by that are satisfied by J, right? So of course the transportation cost can be proportional to the fraction of the demand, and the Dij here are the distance from I to J, right? So if you are shipping some items from I to J, the transportation cost is usually proportional to the distance. Yeah, and now let's talk about the constraints. First, we have demand satisfaction constraints. Remember that W decides the fractional demand satisfied by J. If you sum over J, then that means all the demand have to be satisfied by some depot. And you have to force Wij to 0 if the depot is not built, right? That's what this constraint means. If Zj is 0, then Wij is 0, right? Here the distance is calculated by if you already have the coordinates, you can just calculate the distance using the Euclidean distance. And we also have the bound constraints, and the domain of Zj is 0, 1. That's it. Okay. Any questions here? Yes.
Here, since we are assuming that we don't know the locations of the depot beforehand,
Yeah.
so DIJ is also a variable here.
Yes.
So how well does this problem scale? Isn't it NP-hard?
Yes, I think so. I think it's hard because this constraint is essentially non-convex, right? If you have a Dij, of course, if you put the square root term, it is going to be non-convex. But if you just square on both sides, you write Dij square equals to the these two things squared. You have a quadratic equality constraints, right? And that's also non-convex constraint. Yeah. So this problem is actually very hard to solve, much harder than the MILP version of the facility location problem. Right? Because you allow more degrees of freedom, you can you not only pick the binary variables, but you allow the coordinates to change, right? In the MILP problem, the distance is fixed. Right? Once you pick ij, since the location have been predetermined, the distance are constant. Right? Any other questions here? Okay. Yeah, and the continuous facility location problem is very similar to a problem in machine learning called k-means clustering. So what k-means clustering does is the following. Okay. So if you have a bunch of data points, let's assume the data points are in 2D, and you want to cluster the points into k clusters, right? So the k is a fixed number provided by the user. For example, the user provide k equals to 3, right? So if k equals to 3, then you want to cluster the points such that each of the points is in the same cluster as the similar points, right? The points closest in distance to them. If you want to say that in a very formal way, that means you want to partition all the data points into k subsets such that the within cluster variance is minimized. Right? You can calculate the variance of those points within the same cluster. You want to divide the data points in a way such that if you sum up the variance of the 3 clusters, they are minimized, right? So if you pick the data points such that they are all closest to each other within each cluster, then within each cluster the variance is very small, right? But if you put this data set together with this data point in the same cluster, the variance within each cluster would be large, right? Okay, that's what it means. And this problem can be formulated as a MIQCP problem. Again, there are different formulations to those problems. I'm just showing you guys the most naive formulation. You can always improve those formulations in certain ways. Right? I'm just showing you a very intuitive using the big M type of formulation. And also for the continuous facility location, there are also ways to improve those formulations, but I'm just showing you a very naive way of formulating that. Yeah. So here, the sets are 2 things. One is a set of all the data points, and then we have a set for all the clusters. And without loss of generality, you can always scale the data points such that all those data points are in the range of 0, 1. Right? You can just divide them by the minus the smallest number and then divided them by the range, right? And then in such a way you can scale all the data points to be between 0 and 1, right? It's a linear transformation of the data points. Okay, so now we define some variables. Let's define yik being binary decision variable. It is 1 if you assign point I to cluster k, and 0 otherwise. Now we have di that denote the distance of point I to its cluster center. And ckj being the jth coordinate of the cluster center, right? Since we do not know where is the cluster center, we just calculate that as part of the optimization problem. So CKJ is to be determined. Yeah, is a setup the problem clear? Yes.
I'm sorry, what does P represent?
Yeah, so P represents the data points. So P are the coordinates of those points here.
Oh, so it's a vector class.
Yeah, so it's a vector, right? Each of the P has what? Should be, I didn't denote that. Perhaps should be the J's the J denote the coordinates. So Pj are the jth coordinates of point I. Okay, perhaps let's write it down. Pij is the jth coordinate of the ith data point. Right, and then we scale all the data points such that all the Pij is between 0 and 1. Yeah. Okay, the formulation of this problem is also very simple, but if you actually implemented something like this, it's very hard to solve to global optimality. Let me explain what each constraint means. Right. So the objective is to minimize the sum of distance to the cluster center, the sum of variance. Actually, the distance raised to the power 2. Right? Since we are talking about the variance instead of the standard deviation. If you are talking about standard deviation, you can do the square root of, okay, yeah, never mind. So the di here is not denoting the distance, but is denoting distance squared. Okay, since we are talking about the variance. If we talk about standard deviation, then it's the distance itself. Okay. So here how do we calculate the distance di, right? Or the distance squared? It is nothing but di is greater than or equal to this term here. So let's try to interpret this term very slowly. Again, so ck, remember this ck vector is a coordinate of the kth cluster center, right? And pi denotes the s data point, right? So the distance between the s data point and the kth cluster center is nothing but the sum of this term here, right? But when does this inequality hold? We need to make sure that when this data point is assigned to cluster center K, then this inequality hold. Otherwise, we have a big M to let it hold trivially. So the di only has to be greater than or equal to the distance it is assigned to, right? So let's think about a particular instance. So let's say we have a 2D coordinate. This is point pi, right? And then we have two cluster centers, maybe K1 and K2, right? So this constraint is saying that the di has to be greater than or equal to the distance squared of these 2 points. Right. So the distance are these 2 vectors here, right? So this is the distance to K1. And we have the distance to K2, right? But actually, since we are minimizing over D, we are only going to pick the distance to be the smallest distance, right? Therefore, you would like the optimization model to choose which cluster you will assign Pi to, right? we don't know what would be the best way to assign pi to which cluster. Therefore, we use this binary variable yik to let the optimization model to decide which cluster we are going to assign each point to. Okay. Of course, if K1 and K2 look like this, the optimization is always going to assign pi to K2, right? Since K2 is closer to pi here. But the location of all those cluster centers are to be determined by the optimization model. Therefore, they are treated as variables. We don't know which one the optimization is going to pick. Therefore, we need some binary variables to decide which cluster center we are going to assign each point to. There is a binary variable associated with each data point and each cluster center. That's the yik variable. Yes? Yeah, so this one?
Yes.
Yeah. So this one is to decide, the distance between a point P and its closest cluster, right? So we want to penalize the distance between Pi and the closest cluster. So let's say, for the sake of the argument, let's first remove this big M. Let's first remove the big M, see what happens. Then we will show you why we need the big M, right? So let's say we remove the big M, we'll see what happens, right? Let's say first we remove the big M, right? So then it will be translated into two constraints. That means let's call this point 1, right? The D1 should be greater than or equal to the let's say P1 minus CK1, right? The distance squared, and D1 greater than or equal to P1 minus CK2 squared, right? So if we remove the big M, we will have these two constraints here, right? But that's not the constraints we want, right? If we write these two greater than or equal to constraint, then D1 would be equal to the largest distance over all the cluster centers, right? So if we have a picture like this, then D1 would be the longer of these two distances. That would be be equal to the distance from P1 to K1, right? But on the other hand, we actually want the smallest distance to the cluster center, right? Okay, so therefore, we would like to add some binary variable to let the optimization model choose which of these greater than or equal to constraint is active. We only want one single constraint to be active, which is the cluster center that this point P1 is closest to, right? Or maybe using these two examples, if the coordinate of the two cluster centers are at this stage, we would like D1 to be equal to this length, right? So how to let D1 to be equal to this length? We need to express that using some sort of constraints, right? Essentially, we want D1 to be equal to the minimum of P1 minus CK1 and P1 minus CK2, right? So how to express this minimum over two distance in terms of constraints? It's not that trivial. Therefore, you need to add another binary variable such that the yik is basically saying which of these distance is the smallest, right? So if this distance is smallest 1, then y1k1 is 1, otherwise this guy is 1. That's what we are doing with this big M type of constraints, right? You only let this constraint to to be active when yik equals to 1. Then you let that piece to be active. That's what we are doing. Yeah. Okay. I cannot spend more time on this. You can try to absorb it. Of course, this is not the best formulation. It's just one formulation that works. Okay. Yeah, so I would like to talk about a problem very relevant to chemical engineering. It's called the pooling problem. And if you think about all the oil companies, they are solving this pooling problem every day. It's a so-called $1 billion problem. The idea is that the oil and gas companies will get some materials from the upstream. And then at the end of the day, they want to make things like jet fuel, diesel, and gasoline. Right? If you go to a gas station nowadays, they have gas with different compositions. Right? They call it 85, 87, and 89, something like that. Right? If you go to a gas station. So how to make those gas with different compositions? The way they do that is by solving a pooling problem. You can assume in the upstream, they have a bunch of raw materials with different compositions, and they are going to mix those raw materials in the so-called pools. Right? You can think about pools as a mixer to mix all those upstream materials, and then they are going to split the stream and mix them again to make different types of products. That's how things work. And besides petrochemical refining, there are also other applications like wastewater treatment. Right? You want to guarantee the composition of your wastewater satisfies some sort of constraints. And it also has application in natural gas design. And if you look at this problem, the graph, there are 3 types of nodes in this graph. Those are the input nodes. You have all the raw materials. And those are called the so-called pools where you are mixing those raw materials. And here you have all the products, which you can think about this as the different gasolines you can get from a gas station. All right. Yeah, and in a more abstract way, you can think about the raw materials have specifications, like the sulfur concentration. You want the sulfur concentration to be lower than a certain number, and there are other properties like octane number. Right? But in an abstract way, you can just think about the 2 compositions as red and green. Right? So the inputs will have different compositions of red and green. Right? Then you are going to mix the inputs in the pools, and the pools will have different red and green compositions by mixing the inputs. And then you split and mix them again at the outputs. The output have to satisfy some constraints on the compositions of red and green. Right? For different products, you need different compositions of red and green. Okay. Yeah, that's what this problem does. Then let's talk about different formulations of the pooling problem. Yeah, by the way, the pooling problem is perhaps the most widely studied problem in global optimization. Even if you go outside chemie, the mathematicians have put a lot of effort in studying the pooling problem. This is more like the traveling salesman problem for non-convex optimization, right? A very basic problem here. And the indices include, raw materials, product, and pools, and then we have some specification on the qualities. Right here in the previous slide, the qualities will be the composition of red and green. Right. The parameters are not so important for now. Basically, you have some cost of the raw material, the price for the products, and then you have some upper bound on the availability of your raw material. And then you already know the quality of the raw material. At the end of the day, you would like to satisfy the demands for the products. We also have an upper bound on the case quality of the J's product, and the pool has a given capacity, right? You cannot mix an infinite amount of material at the pools. Yeah. So here we have all the variables in this figure here. Let's assume we have a very simple problem with 2 inputs, only 1 pool, and 2 products. Right? And the x, y, z variables basically denote the material flow. You can think about the material flow as maybe, let's say, kilogram per hour or moles per hour. So the x variables denotes the flow from the raw material to the pools, right? So this is a flow from the first raw material to the first pool. That's why we call it x11, and this one is called x21. So the z variables denote the flow from the inputs to the products, right? So this is z11, and then this is the z22, right? The y variables denotes the flow from the pools to the final products. Right? The p variables denotes the case quality of the pool L from the pooling of raw materials. Right? Since we already know the quality of those x variables, right? So because you know those are the input materials, you assume you already know their quality. That's why for all the x and z variables, they all come from the input materials. You assume you already know their quality, right? But the quality of the y variables are unknown, right? The y variables come from the mixing at a given pool, right? So the quality of those y variables are to be determined by the optimization. Okay, so that's why in the p formulation, we have the quality at a given pool is to be determined. Yeah, so that's why this formulation is called the p formulation. Is the setup of the problem clear here? Okay, yeah. So the objective involves different types of cost. You have the cost of the raw material, and then the profit comes from the sales of the products. Then you also have the z variables are from the raw material, and then the z variables are directly sent to the products. That's why you have this term here. The details you can find it out very easily later. Let's just talk about the important constraints. First of all, we have a bunch of linear constraints that specify the availability of the raw material. Right? For example, here, if you look at the first raw material, the availability of the first raw material is A1, right? Then we have Z11 plus X11 has to be less than or equal to the availability of the first raw material, right? Basically, this equation is sum over all the streams that are sent out from each of the input material. They have to be less than or equal to the availability of the raw material. You cannot send out more material than what you have. Okay, yeah. Okay, and then the second constraint is to specify the conservation of flow in and out of the pools, right? If you look at this particular pool here, the sum of x into the pool has to be equal to what flows out of the pool. This is very straightforward. And then we also have an upper bound on the capacity of the pools, right? So if the capacity of pool 1 is S1, then X11 plus X21 has to be less than or equal to the capacity of the pool here. Okay, and finally, the sales of the product cannot exceed their demands. What that means is, if you consider the demand of product I and you sum over all the flows into the demand, you cannot sell what your customer cannot sell more than what your customer needs. That's what this constraint says. This maintains the quality. Maybe let's not talk about this. So let's talk about the other constraint first. Okay, so this constraint is to balance the quality of the streams at the pools, right? Again, so we assume some sort of perfect mixing, right? If you mix material X11 and X12 at the pools, then you will assume ideal mixing. You fully mix X11 and X21 at the pools. Then what goes into the pool has to come out, right? Then that essentially says, so this constraint, this term denote what is going into the pool, and this denote what's going out of the pool, right? So if you can think about the K as, let's say K can equal to the red and green, right? Essentially, the red component that goes into this pool has to be equals to the red component that goes out of the pool, and so and the same wise for the green components, right? So this constraint is essentially balance the different qualities that goes into the pool and what goes outside the pool, right? Let's say we pick a given L and a given K. Let's pick L to be the first pool and K to be the red pool, right? Red components, red quality maybe. And then this term is denoting the red components that are going into the pool. And then the sum over Y are the flows that are going outside the pool. And P denotes the quality of all those streams that goes outside the pool, right? So this quality can be determined by this mass balance equation here. Okay. Yes.
So C is constant.
Yes, C is constant because C is the quality of the input material. Right?
Okay.
So you can think about C as the red component of all the inputs, right? And all the red components goes out has to be equal to the red components goes in. Right? And that's what this constraint does. Right. So after this is a balance of the red and the greens, right? And this constraint is to specify the quality of the red and greens at the product. Remember that we have an upper bound. In this case, we only set an upper bound of the quality. Maybe, let's say in some of the gasoline station, they specify the upper bound on the sulfur concentration. Right? So you want to make sure that the sulfur concentration at product 1 and 2 are below a certain threshold. That's what this constraint does. If you want to speak that in terms of the red components and green components, the left-hand side will specify the red components going to the product, and they have to be less than or equal to the total flows times the upper bound on the concentration of the red. That's what this constraint does. Okay. Any questions here? Yeah, so the notations might be a little bit confusing. You have to go back and forth, but the logic is, if you think about all this would be all the red components going into product 1, then all the red components concentration has to be below a certain threshold. That's what this constraint says. Okay, so here that's a P formulation. Well, there is another way of formulating the problem, which is called the Q formulation. Then the idea is very simple. You just replace those X variables using a Q variable. The definition of the Q variable is to represent the fraction of the inputs to pool I that comes from, to pool L that comes from input I. Okay. What it does, let's look at this particular example here. Okay, so this is a pool 1, right? And the total flow into the pool 1 is nothing but Y11 plus Y12, right? That's the flow outside pool 1, right? Of course, the total input equals to the total output, right? So that says the total input of to this pool 1 is just the sum of these two variables. And remember when we said that Q11 denotes the fraction of flows into pool 1 that comes from the first input here, right? For example, you can say 30% of the input to pool 1 comes from the first input, and 70% comes to the second input, right? That's what this Q variable does. Then Q11 equals to 0.3, Q21 equals to 0.7, right? So this is equivalent to using the X variables, right? If you use those X variables, then essentially you have X11 equals to Q11 times Y11 plus Y12, right? So here in this figure, we are replacing the X variables by the Q variables here, okay? Yeah, so if you do this replacement, essentially you can replace all the X variables by the Q variables, right? You just do this very simple reformulation, and of course the fraction has to be sum to be equal to 1, right? Because they denote as a fraction. And so this is a Q formulation. You just replace all the X with the Q and Y variables. There's nothing special here. I'm not going to the details again. Okay. And then there's another formulation called the PQ formulation. Yes.
How is Q formulation better than P formulation?
Yeah, so that's a very, very deep question actually. I will talk about that in the next lecture. And then yeah, so the reason you need different formulation is that the convex relaxations of these formulations have different tightness. So the only thing, probably the most important thing in global optimization or MILP is that you want to have a relaxation that is as tight as possible, right? So the reason you want to use actually the PQ formulation is better than the P formulation. The P and Q formulation, I don't know, maybe they are incomparable. I'm not sure. Let me double check. But definitely the PQ formulation is tighter than either P or Q formulation. The reason is that the convex relaxation of the PQ formulation is tighter. Okay, yeah, that's the reason. You will have a better understanding after the next few lectures. Here I'm just showing those formulations. Yeah, that's a very, very good point. Yeah, so for the PQ formulation, we are adding one more redundant equation to the problem, which is the sum of QIL times YLJ equals to YLJ, right? So essentially you are multiplying these two equations. We already have the sum of I from 1 to capital I, Q, IL equals to 1. This is just the sum of all the fraction equals to 1, right? Now let's multiply this linear equation by YLJ on both sides, right? And if you multiply YLJ on both sides of this equation, you get this equation here. Okay, this is a redundant equation to the problem because you can derive this from the original constraints, right? But why this formulation is, the reason this formulation is useful is because if you consider the convex relaxation of those problems, adding this equation will no longer be redundant. That's why we are adding this equation. It will become clear when we talk about convex relaxation. Okay. But if you just consider the non-convex problem itself, there is no difference in those formulations, right? They are all equivalent. Now let's talk about another application very quickly. A lot of the faculty in this department work on things like material design or protein design, these type of applications. And the idea of those problems is just to find the structure of the molecules that minimize the Gibbs free energy, right? from the second law of thermodynamics. Usually those molecules are at the structure with the lowest Gibbs free energy. And they are a very well-known problem like protein structure prediction. The energy function of those molecules are highly non-convex, right? I just took some animation from a paper. You can see they have multiple local minimums, and those problems are usually pretty hard to solve. Yeah, so here I'm showing a very simple energy function of molecules, right? So you have different terms to model the molecules. The first is a bound stretching term. Basically, you are modeling the bound of a molecule as a string, right? The length of the, you have a, how do you see that in physics? Like you have a predetermined length, but if you stretch or bend the string, then you are penalized by like a potential function or something, right? And similarly, you can have a potential function for the angle of the molecule and also the torsion term of the molecule. And this is the term for the van der Waals interaction term. You have this r raised to the power of 12 minus r raised to the power of 6, right? And finally, if you have some ions, there will be some Coulombic electrostatic interaction term, right? This probably look familiar to you. Yeah. Okay. Yeah. Anyways, I'm not a physicist or chemist, but just give you this result for reference. Okay. And of course, this problem is very highly non-convex to solve, right? You have those highly non-convex terms here. Okay, yeah. So finally, I want to spend the rest of the class on this application. So the application itself might not be the most relevant application, but the idea I want to convey with this application is that for a non-convex optimization problem, sometimes if you can do some tricks, you can convert it to a convex optimization problem. Right? So we will show you a trick today called the log transformation to convert a non-convex optimization problem into a convex optimization problem. Right? That's the main takeaway I want to use for this problem. Okay. So the application is called a multi-product plant with single product campaign and zero weight policy. Let me explain what each term means. Okay. So what is a multi-product plant? So if you consider this particular chemical plant here, right? It has several different stages. Right? You can think about each stage as things like mixing, reaction, or separation. And each stage have a number of parallel units. Right? All those units are identical for the sake of the argument. And then you can produce multiple products with this chemical plant. Let's say you have two products, Q1 and Q2. Right? The demand of Q1, let's say, is represented using this circle here. You can split the total demand of a given product into several batches, right? So for example, if you want to produce 100 kilograms of product A, then you split them into equal size of 10 kilograms, right? Then you have 10 batches of product A, right? That can go through this process. And similarly for product B, you can split them into equal sized batches, right? But the batch size is to be determined by the optimization problem. Okay, that's like the setup of this this problem. You just have this multi-stage chemical plant. Then you want to produce multiple products. The product can be split into multiple batches. Each batch has to go sequentially throughout all the. Here we have 6 stages, right? Each of the product has to go through all the stages. And in each stage, you have parallel units. They are all identical. You can just pick an arbitrary one to process that. Okay, that's like a multi-product plant. Now the next concept I want to explain is so-called single product campaign. Okay, so what does single product campaign means? To explain this concept, for the sake of the argument, let's assume we only have two stages, and then each stage only have one single unit, right? Let's say unit 1 is at stage 1 and unit 2 is at stage 2. Right? So single product campaign means when you have demands for product A and B, you first produce all the products A, and then you start producing product B. Right? You are not interchange between product A and B. That's called a single product campaign. So here, let's say we have 2 batches of product A and 2 batches of product B. Let's first produce 2 batches of product A, then we produce 2 batches of product B. That's called a single product campaign. But on the other hand, if you first produce product A and then you move product B here, right? Then that's called a multi-product campaign. You are interchange between product A and B, right? And in practice, there are usually a large number of batches for both A and B, and then you can just keep producing product A, and after you are done with, let's say you have 100 batches of product A, and then you produce the next maybe 200 batches of product B. That's what in practice happens. Okay, so next I will explain a concept called cycle time. Okay, so if you consider these 2 units here, how often can you get a batch of product A? Right. So let's suppose for unit 1, it needs 2 hours to produce a batch, and then you move this batch to unit 2, and by unit 2 we'll need 4 hours to produce this product, right? And then unit 1 have to wait for 2 hours here, right? So this will be the 2 hours, because unit 2 are like the rate limiting step in this process, right? It needs 2 hours to produce a batch, but unit 1 only need unit 2 need 4 hours, unit 1 only need 2 hours, right? So therefore, if you have units with different production time, then essentially you are limited by the rate limiting step, which is unit 2, right? So you probably need 4 hours to get a batch of product A ready, right? Since the production time of unit 2 is 4. Okay, so you can generalize this by saying that the cycle time for product I, denoted as TLI, is a maximum of processing time over all the stages, right? If you have 6 stages, then your cycle time is limited by the maximum processing time over all the stages. Okay. Yeah, and similarly, the cycle time of product B would be 4 as well, right? Since it's limited by unit 1. Okay. That's called a single product campaign, and then you can get the cycle time of product A and B. Okay, so the next concept I haven't done is so-called zero wait policy. So zero wait policy means once I produce product A in the first stage, I have to immediately move to the second stage. That's called the zero wait. On the other hand, if you have some storage in the first stage, then you do not have to do the zero wait, right? You can first put the product A aside after the first stage, and then wait until the machines at the second stage is ready, right? So zero wait policy is like after you are done at stage T-1, you immediately move to stage T. That's what is called a zero wait policy. All right. Questions related to the problem setup. Okay. Yeah. So the next thing is, if you have multiple units at each stage, then the cycle time is determined by the maximum over the processing time on a single unit divided by the number of units at that stage. right? Let's assume you have 3 units in this particular stage, then you can run things in parallel, right? Then the cycle time of a given product would be the processing time divided by 3, the number of units you have, right? And that reduces the cycle time, right? Here in this case, we only have 1 unit per stage. That's why you just pick the maximum over Tij, but if you have multiple parallel units, you divide them by the number of units, okay? Yeah. So the problem is very complicated. I studied this many years ago, and then I stopped studying this problem. I forgot what a single product campaign is, right? But the idea is to give you some sense of how to translate a non-convex problem to a convex problem. That's the main takeaway rather than the problem itself, okay? Yeah. So the stats are products and the stages. The parameters given are processing time of product I in stage J, and Sij is a sizing factor for product I in processing stage. That means in order to produce 1 kilogram of the product, the volume of the reactor that you need. Right? So let's say if in order to produce 1 kilogram of a given product, you need 3 liters of reactor volume, then the setting factor is 3. Okay. And Qi denote the demand of the product. Alpha and beta denote the investment coefficient and exponent for purchasing the units, or I use the word vessel at stage T, right? You need to purchase the vessel at each stage. Like the vessel can be reactors or maybe distillation column or membrane separations, right? So usually when you calculate the investment cost, there is a constant term here, and the exponent is usually some numbers between 0 and 1, actually strictly less than 1. Why is that? Because economy of scale, right? Usually the equipment does not scale linearly with respect to size. They scale like sublinearly, right? And H is the planning horizon. The goal of this problem is that you want to minimize the investment cost of a multi-product plant such that you can satisfy the demand of all the products within a time horizon, right? Of course, you want to minimize the volume, make the volume as small as possible such that you can still satisfy the demand. Yeah, and the variables to determine are the volume of each unit at stage J, the size of each unit J, and then the number of units for the parallel units at stage J. And we also need to decide the batch size of product I. Remember that we are splitting the demand of all the products into several batches, right? We also need to determine how we are going to split them. And TLI is a cycle time of product I. Okay, so let's first formulate the non-convex optimization problem using those variables and parameters. Then we will show you how to translate that into a convex problem. Yeah. So the objective is to minimize the investment cost of all the vessels, right? Remember, N is a number of vessels you are going to purchase at stage J, and beta are like the economy of scale type of exponent, right? Remember, beta is strictly less than 1, right? And in that case, if you take the second order derivative, this is a non-convex function to optimize, right? Okay, so if beta is greater than 1, then you have a convex objective. Beta is 1, it's a linear. If beta is between 0 and 1, then this is not a convex problem. Okay, yeah. So this is a non-convex objective you have. And then the constraints are also non-convex, right? So let's look at each constraint. The first is the vessel size constraints. It's a linear constraint. So recall that BI is the batch size of product I. Sij is a sizing factor, right? So in order to produce batch BI, then the volume of the let's say the vessel has to be greater than or equal to a sizing factor times the batch, right? As you can imagine, as the batch size grows, the volume of the vessel has to grow as well, linearly in this case. And the cycle time is greater than or equal to the processing time divided by the number of units. Okay. We already talked about that. And in this case, although it is a nonlinear constraint, it is convex because we have 1 over n. 1 over x is a convex function. Okay. Yeah, but the last constraint is non-convex. The last constraint is specifying all the orders have to be completed within the planning horizon. Okay, so the demand for product I is Qi, right? So we have Qi divided by the batch size equal to the number of orders, right? So, then the number of orders times the cycle time of each batch, and then you sum over all the products, they have to be less than or equal to the planning horizon. That's what this constraint says. Okay. So this part is the number of batches, right? And each batch takes cycle time TLI, right? So the number of batches times the cycle time equal to the total time for a given product. Okay? And then we have variable bounds. Right? So with this formulation, as you can see, we have some linear constraints, but this constraint is non-convex because Q is a variable. Oh no, not Q is a variable. TL is a variable. B is a variable. Then you have the the linear fractional term. Right? This is a non-convex constraint, and then the objective is also a non-convex constraint. Right? So now I'm going to introduce a trick that can reformulate this as a convex problem. Now the idea is we are going to take a log transformation of each variable. In other words, remember we have all those capital V, volume, the number, the batch, and the cycle time. We are going to define some lowercase Vj, Nj, Bi, and Tli. And those lowercase variables are the log of the original variable. Okay. In other words, the original variable is an exponential of the lowercase variable. Okay. Yeah. So this is like a one-to-one mapping. So since all the variables are non-negative, right? Then you take the log and exponential. There is a one-to-one mapping between all those variables. If you get those lowercase variables, you can always map it back to the original variables. Okay. The only thing we need to take care of here is the Nj variable determines the number of vessels per stage. So this Nj is an integer variable. But we can always expand an integer variable using some binary variable, right? So the Yjk are some binary variable, and then the sum equals to 1 to determine the number of vessels at a given stage. Okay. So you can say K, at least you need one vessel. Let's use this n bar j as the maximum number of units you can have at a given stage, right? So if you have this nj term, essentially we are forcing nj to be an integer number that is between 1 and nj bar, right? So nj bar can be the maximum number of units you can have in a given stage, right? And then you can always encode an integer variable using binary variable, right? So nj to be the sum over k times the yjk, and you only let one of the yjk equals to 1, right? It's like choosing an integer number between 1 and nj bar. That's what this constraint does. Now with that, you can also embed this lowercase nj by taking the log of k, right? Since the lowercase nj is a log of this term, right? Then you just take the log of k in each of the term in the summation. Yeah. Okay, so now we already did a variable transformation. The next step is to plug in this transformation into the original problem and see what happens, right? After you do that, you find, some magic happens and you transform the problem into a convex problem. So let's try each of these constraints, right? Remember the objective is capital Nj times alpha j times v raised to the power of beta j. Okay. Now you replace this capital Nj by e raised to the power of lowercase nj, right? Remember all those terms are log transform, or then you just replace those capital variables with e raised to the power of lowercase variables. Then since those two are two exponential terms, you just add them together, right? And then we know that all the exponential functions are convex functions, right? So you transform the objective into a convex function. And what about the constraints? You can try the same trick. So this is a linear function, and you can take the log on both sides. Why you can take a log? Because the log function is a monotonic function, right? If Vj is greater than Sij times Bj, then we know that the log of Vj is also greater than or equal to the log of Sij times Bj. If you take the log, then we basically get those lowercase log transform the variable, right? And since Sij is a constant, this term is a constant, and all the rest are linear. And similarly with this term here, you can transform it into a linear term, okay? And this term is originally it is the non-convex constraint, right? You have the TLI divided by BI. But with this log transformation, it becomes convex. Again, it has an exponential term, right? So with those log transformation, basically we transform all the constraints from non-convex to some convex constraints, right? At least the relaxation of this problem is convex. Then you can take advantage of the convexity to solve this problem. Okay, that's just a trick I want to introduce here. Any questions? Oh, all right. Yeah, so here's all the formulation. You can also add some non-trivial variable bounds to those problems. Yeah, so here's all the references we have. There is not a single book in global optimization that covers everything. Notably, the first reference is written by Professor Tavamalani. Maybe some of you know him, right? Some Professor Agrawal students may be working with him. Actually, he, his PhD thesis became a classical reference textbook in global optimization. Like speaks of how smart he is. He's a professor in the business school at Purdue now. Okay. And then the Haust and Tui book is another classical reference in global optimization. The k-means clustering is from the reference by Papageorgiou. The packing problem is from this reference here, and then the pooling problem is from these summer school slides. These very very nice trick of convexification is from the paper by Grossman and Sargent. Okay, yeah, so that's all I want to talk about today.